talk about succinct arguments. So these are proofs where there is this conversation between a prover and a verifier, where the prover is trying to convince the verifier that there exists a witness that satisfies a particular relation. For instance, trying to prove that they know an input for which a circuit is satisfied, a transaction is valid, etc. And here, argument means that the security of this protocol holds computationally, like on the discrete log assumption. And succinct means that the verification time is sublinear in the size of the witness. In particular, we will focus on preprocessing succinct arguments, which means that the verification time is not only sublinear in the size of the witness, but also in the size of the statement. So we can get very, very efficient verifiers. Why should we focus about trying to make provers that are efficient with large instances? Because while over literally the course of decades, we were able to improve a lot in time, in both proving time and verification time, we kind of hovered space complexity to the point where right now, if we try to prove billions of gates, circuits with like billions of gates, it's literally not possible to do it. I'm talking about modern proof systems like, I don't know, Marlin or Spartan, or even bulletproofs, or like Plonk. And so as an example of why this is sort of practically relevant, already the compression function of SHA-256 is about 30,000 constraints. And if we are, for instance, trying to verify a transaction, so like maybe we have a Merkle tree with a bunch of these compression functions, then we're already far outside the benchmarks that we put in papers. And if we have a lot of them, for instance, when we do ZK rollups, we're already far outside what we can do in modern implementations. So this is sort of the core motivation of our work. And also, besides like ZK rollup, you can think about, I don't know, proving that at 0 day is valid, or like very, very large circuits. And the literature on trying to make these things possible has to deal a lot with space efficiency, because space efficiency is really the bottleneck here. And there is some literature that is, for the most part, like TCC papers, so very, very theoretical. And these are like follow different approaches. One of them is using full homomorphic encryption, so definitely not in sort of the practical spectrum. Another one is using recursive proof, and so doing so-called incrementally verifiable SNARKs, and so doing complexity-preserving SNARKs. So proofs that sort of preserve up to a polylog factor space and time of the initial computation. The idea is that you take a circuit, you chunk it up in little parts, and then you make proofs of these little parts, and then you sort of aggregate all these proofs together. But even here, you have to put part of the verification circuit in the prover, so you incur in extra overheads. Another approach that has been sort of open more recently is about streaming. And this is the one that we will focus on. The idea is that in now the prover, you're trying to build a proof, and the prover does not have random access to its input. It has instead streaming access. It means it can read sequentially the inputs and then produce a proof in small space. In practice, I would like you to think about a prover that can read sequentially from a file, so not random access, but runs this computation in small space and then produces a proof. Or you can even think of potentially making a bunch of passes over this initial input, or even downloading it from the internet. And so what we found is that there are like these two directions in the literature. Either you can get very fast provers, or you can have these sort of theoretical results where you have like space efficiency. But there is really no middle ground. So what we did, we introduced this idea of elasticity, which is that there are provers that admits two different implementations. One that is space efficient, one that is time efficient. At the end, they produce a proof, and the verifier couldn't care less about which configuration has been used to run this thing. We also prove that this thing exists. In particular, we prove that there exists a preprocessing succinct argument, so with very fast verification, for circuit satisfiability, the best that you can do, that has two possible instantiations. One that runs in linear time, the best that you can do, and one that runs in log space. And despite both results were sort of already known in the literature, it was not known that you could do both at the same time, and even less what were the complete performance of this thing. In addition, we sort of advanced the state of the art in space efficient provers, showing that for very particular instances, depending on how the R1CS matrix is formed, you can also have lower the time from n log square n to n log n. Again, the verification is, the verifier runs in log time, and the proof is independent from the instantiation of the prover. The way that our theorem works is that using the sort of IOP paradigm of creating an idealized protocol, where we have sort of the prover and the verifier interacting, and the prover sending either oracle messages or normal messages, and then implementing parts of this protocol using polynomial commitment schemes. And we have this theorem, this cryptographic compiler, that says that if you have, well, an elastic theoretical idealized protocol and an elastic polynomial commitment, guess what? You can get an elastic argument at the end. And so for the remainder of this talk, I'm going to concentrate on these little two components and give you an overview of how this can be done. Our theorem is for R1CS. So this sort of matrix relation where the prover is trying to prove knowledge of these, prove that there exists this vector Z that satisfies this matrix vector product. The sort of circle here is the Hadamard product. And it's sort of one of the most used forms of for expressing circuits. But there is really nothing that I think would block it from applying it to other forms of arithmetization like Planck. And but the problem now is, how do you express this in a streaming fashion? What does it mean to stream an R1CS relation? And we sort of define it. Streaming an R1CS relation for us means streaming Z. So giving Z, each element of Z one by one. Now, we also have to stream the matrices, but now we have two dimensions. And we say that the prover can either access them in column major or in row major, the sparse representation. And we also demand the computation trace. So the product, the matrix vector product AZ, BZ, and CZ, which is a vector, so we stream it in the same way as we stream Z. In particular, we have this notion of composability of streams. So if you have a stream A and a stream B, you can create a stream C by sort of using the two initial streams. And for particular instances where this matrix vector product can be done efficiently, imagine like a diagonal matrix, because there it can be done, for instance, in a small space, then these streams can also be generated artificially by composing the initial streams. So the idealized protocol is pretty complex, so I will focus only on one particular subcomponent there, which is the inner product protocol. And the inner product protocol is sort of the cornerstone for a lot of designs of SNARKs, because if you think about R1CS, you have all these linear operations, so it's only natural that the inner product pops up. And so again, here what we want to do is create a protocol where the prover shows that there exist two vectors, f and g, such that their inner product is equal to some y. And what we prove in our paper is that this can be done in an elastic way. So inner product can be proven with a time-efficient implementation that is linear, so the best that one can hope for, or in a space-efficient manner, using only logarithmic space and n log n time. Now, here I'm only talking about field operations, so there is no group involved for now. What we remark is that a lot of already existing protocols, like the sum check protocol, or like bulletproofs, or like these folding arguments, that have this recursive structure where they go from an instance of size n to an instance of size n divided by 2 and then invoke it recursively, they are already elastic in a way. All these protocols have this sort of paradigm where the prover at every round is receiving some randomness from the verifier, and then is creating a message that is being sent to the verifier by sort of folding the initial vector. For instance, in our case, we will fold the initial vector using even and odd decomposition. So we take even and odd, and we sort of squash them together at each round using the randomness given by the verifier. And then we have this new vector that has half the size, and then we use some new randomness from the verifier, and we go on and on until we get a vector of length 1. And this vector of length 1 is sort of very small, no? And can be checked immediately by the verifier. And in particular, is also related to the initial polynomial, to the initial vector. And I'm not going to go into the detail, but can be seen as a multivariate polynomial evaluation of the initial polynomial. What's the cost of computing this if we had random access to it? The cost is linear, because at every round I'm doing half multiplication and addition. So it's n divided by 2 plus n divided by 4 plus n divided by 8. This is a complexity is O of n. But it's not as clear how to do it with space, how to do it in a streaming way. And so our contribution is to provide a streaming algorithm for that. And the idea is that now you do not, to generate these foldings of these initial vectors, you have them accessed as a stream. And the prover, what it would do is it will keep a stack where it would load this information little by little. As soon as there are two elements that are at the same level, we'll sort of fold them together using the randomness of the verifier. And then replace the two elements in the stack with that particular folding. And it will continue like that. As soon as there are two elements of the same level, they get folded together. At the end, what do we get? We get a stack that can only grow logarithmically, because there are only log levels. And in addition, how many operations are we doing? Well, we're doing only linear operations, because again, we're doing n divided by 2 addition and multiplication, plus n divided by 4, plus n divided by 8, so on and so forth. So overall, because we have to generate the foldings at each layer, we have an overall log space complexity and n log n time, which is what I promised in the theorem. But in addition, our particular protocol has this very special structure, that it is possible to fix a memory budget, so fix a threshold, and then you can run the streaming algorithm for the initial vectors. And once you reach a certain threshold, like an instance that you can fit into memory, the prover can just stop, write that instance in memory, and then proceed with the time-efficient algorithm. What does this mean? It means that you can literally prove an instance of an arbitrary size, just let the prover run, and as soon as this instance fits into memory, which was already the case in the past, then you can run with the best known algorithms in the literature. And so this is an approach that doesn't in any way doesn't hinder what was already achieved in the past. At the end, clearly the verifier has to check that all these foldings have been done correctly. And so I mentioned that this final vector is related to the initial one because it can be seen as a multivariate polynomial evaluation. And the way that we do it in these sort of idealized protocols is that we consider that the verifier has access to this magic oracle to which it can ask for an evaluation of this polynomial. But in practice, what we really do is that we send a commitment to this polynomial, and then we send back an evaluation together with a proof that the evaluation was done correctly. What we do in our paper is we also provide a way for, instead of doing multivariate queries, doing only monomial queries. Why should we be interested in doing only monomial queries rather than multivariate? Because we know of very efficient algorithms for univariate, for the univariate space. In particular, our protocol is using KZG, so constant number of pairings. And our protocol here is sort of generic. Anyway, if anywhere you have you have a multivariate protocol, you can transform it in a univariate. You can transform it univariate and so use KZG as long as you're happy to have a trusted setup. Okay, and sort of diving more into what we do in the polynomial commitment at the polynomial commitment level, which also again must be elastic. How do we achieve it? Well, in KZG, if you remember, you have this trusted setup where you produce these sort of powers of an element that is only known to the trusted dealer. And in order to commit to an element, you just take the product of the coefficients of f together with these powers in the CRS, in the committer key. So in a streaming fashion, it's sort of natural to imagine that if you have all these elements of f and all these elements of the committer key, you can just generate the commitment using constant space by accumulating all these elements and sort of getting them one by one. In practice, what we do, however, is we use multiscalar multiplication in batches. So you really fix a memory budget, and then you sort of run multiscalar multiplication over those. one could also imagine using a hardware accelerator. There are other ways for doing so, but sort of this is what happens right now in the implementation. In order to generate an evaluation proof, at least the one commits to the quotient. At least the way that I see KZG is that you take f, you do Euclidean division by a polynomial x minus alpha, you obtain quotient and remainder. The remainder is the valuation of f in alpha. This is evident if you look at this equation modulo x minus alpha. And so the quotient is a sort of a proof because the verifier using a pairing can check immediately if this equation holds. And generating the quotient is really the hard part of a space-efficient algorithm for evaluation proofs in KZG. And to do it, actually, it's very easy. It's something that we learn in high school, and it's Ruffini. So you would take the stream of f, and then to generate the quotient, you just have to keep in memory the previous position. And just apply the law over and over, and then you will be able to produce at the end an evaluation proof using constant time. So really, the polynomial commitment scheme can use very low space, assuming that you have streaming access to the inputs. So you have this entire pile of protocols at the end, and you need to implement them, no? And so that's what we do. We have these sort of protocols for commitment scheme. This protocol that allows us to convert multivariate queries into univariate queries. Then we have this inner product protocol. And in order to be able to build a preprocessing SNARK, you need to also have other protocols. There are like other subprotocols that I didn't show here for reasons of time. And now that you sort of build all these protocols, you not only have to do them space efficient, but also time efficient. So like this was quite a big engineering effort that has been put into arkworks, and you can access it through this URL. And some parts of it, like some subprotocols or the polynomial commitment scheme, they have been brought to the sort of a more generic arkworks grade. And for instance, for those willing to contribute to arkworks, right now in the polynomial commitment library, there are like 3 different implementations of KZG. And it would be nice somebody would, a good first contribution to arkworks could be, for instance, to sort of merge all these implementations together and find what can be put in together. And sort of on a more like implementation and detailed implementation side, for us, streams are only iterators in Rust, literally. And because of the very strong type system that Rust has, we end up having to embed the whole tree of computation that we are doing on these streams inside the type. This means that we have this sort of very generic interface, but and rather than using, for instance, like Rust async, we really go down for like implementing these very specific traits. And at the end of the day, we gain a lot in performance. But the downside is that we have this whole computation tree, which are like very big types into our protocol. And so just to give an idea of what we can do once we have built these implementations, we try to run some benchmarks. And while like in previous works in the literature, generally you would sort of stop at 2 to the 20, like at millions of gates. In our case, we can go up to 2 to the 37. This is like statistical security parameter size. And in particular, yeah, for the non-preprocessing protocol, we can prove hundreds of billions of gates. And even if we try to run our own time-efficient protocol on and try to see where it sort of stops due to problems with memory, it sort of stops at 2 to the 37. So even on our side, trying to make efforts to sort of reduce space, this is the best we could do. And so all that you see here from 2 to the 27 or up until 2 to the 37 are is a space that can only, we believe, be explored through streaming techniques. If we run the preprocessing protocol, we have sort of similar results. But I wanted to open a parenthesis here because I said that the runtime is n log square n, but this is a straight line. And the reason for that is that the bottleneck in all of these protocols are, at the end of the day, the multiscalar multiplication, which are always linear. And so the problem is that if you care about all these constants, about these logarithmic factors, they don't kick in for such long sizes. So maybe they're not that relevant. The problem right now is really all this multiscalar multiplication that we're doing in our SNARKs. And something similar also can be observed in memory. if I set a memory budget, I can really prove an instance that is very large using like less than 1 gigabyte, around like 500 megabytes of memory. And this is completely arbitrary. I could put it less, just increasing the computation time. And even here, even the sort of asymptotic factors are logarithmic. If I set the memory budget correctly, I end up in a sort of plateau where like the memory is really what I fixed it to be. And sort of that's also what's very nice because yeah, if you care about those constants, you should also care about the concrete factors.
Yeah, so there's a question. Why do you need the trace and sparse matrices for the streaming of an R1 CS in Gemini?
Why do I need this sparse stream of
Why do you need the trace and sparse matrices for the streaming of an R1 CS in Gemini?
I don't need the trace, so I don't know what. I don't need the trace of the matrix. I need the row and column. So I need a stream of the matrices. Otherwise, I wouldn't be able to do anything. I need them in a dense form because otherwise the complexity would be n square. And so I need to have this was sort of observed also in the past. If you look at other papers, for instance, Marley, we always think about these matrices in a dense form because the number of non-zero elements, they are the number of multiplication gates. And unless we accept to have this dense form, then we have to come up with the fact of having a square complexity. If we have them in dense form, then we can go down to n plus m, so the number of gates and wires of a SNARK. Yeah, you go.
How does the time complexity and space efficiency of elastic implementation compares to Plonk?
We didn't. So we do not have an implementation that. So I don't know if the question is about asymptotics or concrete complexity. Our protocol is for R1 CS, so we would have to go down and check how this thing can be done in Plonk. But what I can say is that I believe that sort of the same complexity applies at the end. And why am I saying so? Because if you look at the protocols that we have to implement, we have inner product, which is sort of a big part of what you need to do in Plonk. And then you have the lookup protocol and elastic run product, which are the two other components that are sort of necessary in order to make Plonk work. So I think all the ingredients are already there if we wanted to make this thing work with Plonk. And I think the concrete time efficiency and space efficiency would be the same. But nothing is there yet, so it's only speculation. Yeah, I didn't.
Do the elastic lookup protocol, elastic run product also interact with R1 CS?
Yes, specifically, we use the lookup protocol in order to obtain the elements of Z in the R1 CS matrix by the non-zero columns and the non-zero rows. So the way that we prove R1 CS with preprocessing is through a lookup protocol. So they're interacting at the sort of in terms of inputs. They are related, but internally the lookup protocol is a subprotocol that even in implementation has its own folder and it's by itself. Yeah. Go.
Is the tensor check protocol useful for anything besides just obtaining a multivariate?
Yes and no. Like, well, it's already enough, no? Like, it's already a protocol that's solving the issue of how can you relate multivariate evaluations with univariate evaluations. But more in particular, all multivariate evaluation can be seen as an inner product of the coefficients of the polynomial together with a tensor product. That's why we call it a tensor check. So it can be used for any inner product that is of a particular form. Yeah, and sort of wrapping it up. So like what happened in this talk, we introduced this idea of streaming, which is literally about having a prover that can be run either time efficient or space efficient. We sort of put them together and we show how they can be implemented in practice. Thank you.